And as I've mentioned before, as we subsampling the input features, it kind of helps decorrelate the trees, and therefore very likely you're going to have drastically different set of trees, like different trees for, let's say, for each of your bag. And actually, if we think about, so then how to derive the prediction for regression and classification, as you can see from the formulation, it's nearly the same. The only difference is like, what is the set for each bag? In this, I use P to denote the set, maybe like the number of features out of n features, and B here is like for each bag tree that that is learned using like a subsampling training samples. So the only difference between random forest and the bagging technique is the fact that the random forest will have some kind of feature selection procedure in a way, in the way that it's creating or building the tree. Shall we move on? So this is, it is because in the textbook, I'm not sure if I mentioned which textbook I used, but anyway, in the textbook they use notation M for the number of features that I choose, and P to be like the size of the input feature. But in this presentation, I use P for the number of features that I use, and N as the size of the full set of features. So it's slightly different, just letting you know. According to the textbook, it is said that actually if P is about square root of N, you normally get a good result. But I put this way, I think this is depending on your training data. It does not necessarily being this number, but I mean, you can do some kind of validation to check if this number is good for you. But it's like a rule of thumb that we choose this one. The next algorithm is boosting. And as I mentioned before, boosting is about kind of like once we have a tree, we learn to improve it to be better over time. And then that improved tree is actually built on a set of samples from training that we select. And then we repeating the process over and over again. So I will show you the procedure first before we come to this, because actually this notation of summation and the majority vote here could be very misleading in a way. Actually, in the boosting algorithm, the summation should be replaced with something like aggregation, because how should I say it? For regression, you will use summation as in summing or averaging the result of each tree, like when you do the bagging. But for classification, when you do majority vote, actually you will do majority vote of the union of the trees that you get, like a union results of the tree that you get. Like you collect the samples, you collect the output from multiple trees, you put it into the same set, you union them, that's what is meant. And then you find a majority of them. So that's union. So aggregation is better. Another thing, before we move on to how it works, is the notation like that is used to suggest that we actually do some kind of learning. And yeah, let's start. Actually, what I did wrong in these slides is the fact that actually I should use how should I say? Actually, this should not be like a whole entire set of your training. Each time it should be like subset of your training, like when you bootstrap them. It's like it should be one of your bag, like the one bootstrap set. Okay. Actually, it just turned out that as I would describe, you may find that actually this is not very important, whether or not I write it as 1 to M or as a bootstrapped training sample, because what is really the gist of boosting regression is about the sequential learning. Anyway, let's imagine that suppose that I was able to feed in a set of training sample, and this set of training sample could be subset of a bigger training sample. It doesn't matter, because if you like do the bootstrapping, that means each time you get different set of samples anyway, but you just bootstrapped it from the bigger one. Okay. For a set of bootstrap sample, then you will start initializing the boost tree. And this boost tree will be initialized as 0 as first, like it will not give you any prediction. By the way, I forgot to mention that this is a boosting tree algorithm for a regression task. So at the moment, aggregation will just be summation, but we will see what it does. Okay, since the boosting tree is said to be kind of like improving the performance of the previous tree, when we say anything like this in the sense of machine learning, usually that means that we will be involved with something called residual. So in this case, they initialize residual as the target label itself, because it is like, because we initialize this as 0, that means there's no effect from the boosting tree yet. And we only kind of like having this residual to be the target. And if I wrote it like this, that means if I have, let's say, 100 samples that I get from the training data, if my M is 100, but this M could be came from like a bigger training set, let's say, maybe that training set has 10,000 samples. Let's just assume this way. Is that okay? Okay. For this 100, that means that I have to initialize R1 up until R100 to be the same as Y1 up until Y100. Is that alright? And that also, okay, so that is what is meant at the initialize phase. First step that I would do is that I will learn what we call a weak learner, or it's actually a very simplified decision tree. Actually, in the graph that I would show you as a result of this procedure, they only use a decision tree with a width of 1 or 2. That means you only make like one decision and that's it, or 2 decisions and that's it. Okay, your tree might look like that, or maybe look like that. That's what is meant. So, first time you use that 100 samples to train the weak learner. And what you get is like, you get, maybe if you initialize it as, maybe the simplest one is like just width of 1, tree width of 1, a very simple tree like that. And don't forget that whenever we have a tree like this, what we have with it is like the thresholding value. Right, so this is your beta. So your beta is just like a in a value, a scalar value in real space. Sorry for my wording. And yes, and a tree that is like that. And then what you need to do next is to update the boosted tree. So right now your boost tree, as we know from previously, that was initialized as 0, now is, okay, this is still 0. But what you get is like, you get the boost tree equal to lambda time the decision tree that you get. Actually, this lambda here is called shrinkage parameters, but what does it mean by shrinkage parameters? What it means is that it's like, it's weighing whether or not the result from this weak learner is important. So it weighs the importance of your improvement in each time. Okay, once you weigh your learner performance, then you use that learner, your now new boosted tree, to provide the result. But look at the fact that as you provide the results from this weak learner, you then compute the residual, which is the difference between your target and that result from boosted tree. In your next iteration, what you would do is that you would use this residual to now be your target. But this is like the residual and the same input that you learned from, that you used in the previous iteration. So that means that you are fixing your input information. But what you are learning for is like, you are learning for the residual to be smaller and smaller in each time. And it should be smaller and smaller in each time, because that, like, each time that you get your result from the weak learner here, it should, like, be improved, and that improvement should be somewhat closer to your target value. At the end of the day, what you get in this procedure is your F-boost that you actually can also copy from this line. Or on the other word, you can write it as a summation. But don't forget the fact that your first iteration, that will be 0. So, sorry, not that one. I mean, this one will be 0. This one will be your first one. So that means that in order to, do the summation like that, that means you have to append your classifier each time you learn it, and then do the summation of the result at the end. And as you can see, the shrinkage parameters here will control how much each of the weak learner would contribute to your final result. And do not forget that whatever we're doing here, we're doing only over one subset of your training samples. So that means that at the end, if you combine this with the backing, the back trees, this means that at the end, whatever boost tree that you have here, you still have to average it with other boost tree that came from other training subsamples. So at the end, you should get something like if, I'm not sure how to write this one, but it's probably just like what we wrote before, like if maybe if back. Here I use superscript B to identify the boost tree that is learned with each like a subset of the training that is backed. So in this algorithm, as you can see, it seems like the backing wasn't really contribute a lot to the entire algorithm. But what is actually being like a major improvement is how you make your weak learner become better and better in each time. And actually it's better in a way that you summing over each weak learner, but each of these weak learner is learned with the residual that should be less and less and less each time. And this is for regression. Next one will be for classification. Actually, what is difference between regression and classification is just the aggregation function here. So instead of saying that we sum it together, we just aggregate. That means we just union. We just collect it, append it as part of the set of your boost tree. So your boost result will be like, let's say it's like a union. We may, like union of lambda ft something like that. Or on the other word, it is like lambda f1, maybe lambda is f2, and so on. That is one boosted tree. And again, whatever you get here, your result will be the majority vote. So that means if you using this with the, let's say with the backing, that means that you are union over many weak learner. Because this one will give you a set of weak learner. Another one will give you another set of weak learner. Yeah. And here's are some results that if you are using the boosting with different depth of the tree, like the first one is like what I just said, that it's kind of like the tree that look like this. But your second one would look like, like your weak learner will become somewhat smarter as it makes like a double decision. And as you can see, sometimes you are boosting with a very minimal depth here could sometimes perform better than the one that is more complicated. And actually, the green line here is the one that is the random forest. The random forest has a very high error, and that could still be because of the fact that, it's like you are learning your tree based on the subset of your selection of the feature. It doesn't guarantee anything, it's just, choosing. So that's why the boosting algorithm can perform better because there are some optimization phase to make it better with the residual each iteration. Yeah. And actually boosting becomes something that is very important later on, especially when it's come to the algorithm called GXBoost. Actually, before I finish this, I will just give you a little brief idea of what is the gradient boosting. It's very simple actually, because all you change with the gradient boosting is just one line. That is, when you update the boost algorithm, the weak learner, you are actually using the gradient computation to replace the weak learner that you learn with the residual. So in overall, it kind of look like that. So instead of feeding residual into training directly, this one they actually use the residual that is like a gradient of your loss function. You can think of the fact that your loss will look like a, let's say if it's mean square error loss, it look like a quadratic curve where you probably able to find the gradient that will lead to the optimal solution. And with that residual that is like being symbolized by the gradient of your learning loss, you use this residual as part of your training for the new model. And once you have this, you can now aggregate it as your new boost tree. The difference between this algorithm and the previous algorithm that I mentioned is only this. But the thing is, sometimes people actually further optimize the shrinkage parameters by performing optimization on the parameters itself with the loss function. Let's say if your loss is square error loss, so that is like, it would turn into some like a linear regression task, because your parameters will just be like a variable that is part of the equation, and that's only like a, like it's a scalar to multiply with the term. So that's pretty much it. If I remember correctly, it's just that. But if not, I think some people actually replace this with some kind of solver. It's like if you cannot really derive the closed form solution, but it should not be too heavy to compute, since first of all, your loss function, in this case, that is regression, is just like, like mean square error. That should not be too difficult. If you have lambda here, this lambda is only like a scalar value. So it's not a linear regression, it's something else, but not too difficult to compute. You're probably able to find like a closed form solution for it. And that's it. Actually, you can also put this step into what we've learned previously. Like for example, if we think about the regression tree, we can add like a step to optimize for lambda in each iteration here as well. Yeah. Because in this, it's like you kind of fix the update for your boost tree. But here you kind of optimize the step so that it can be well adjusted with your, maybe the differences that is made by the fact that we've learned the new boost tree. Yep, so that's it, the idea of the gradient boosting. At the end here is a summarize of what are these three techniques. The backing is about random sampling the training set. But problem with backing is like, because we still use the same set of input features, very likely all the trees that you get are going to behave in the same way. So that's why people improve a new technique called random forest, where they will actually subsampling the input features so that they can decorrelate the similarities between those three. And finally, boosting is like another concept where you boost the performance of your weak learner over iteration. And you can still use the concept of backing on the top of that. That is, the backing may be used to provide, like a subset of your training to improve the weak learner. But at the end, as you aggregate the result, you probably have to perform something like a union, and then majority vote, or summation, and then average. That's it. for today.